Yes, a 15 kilovolt power transformer can be used mounted on piers for the distribution of power on ships or vessels. There are some key considerations. Firstly, isolation. The transformer must provide proper isolation between the primary and secondary windings to prevent electrical hazards. Secondly, voltage. The transformer's voltage rating must match the distribution system on the ship. In this case, the transformer should have a 15 kilovolt primary winding and a lower voltage secondary winding suitable for the ship's electrical equipment. Thirdly, power rating. The transformer should have an adequate power rating to meet the electrical load requirements of the ship. Fourthly, environmental conditions. The transformer must be designed to withstand the harsh environmental conditions on ships, including moisture, vibration, and temperature fluctuations. Fifthly, safety features. The transformer should include safety features such as overcurrent protection, grounding, and fault detection to ensure safe operation. There are advantages of using a pier-mounted transformer for ship power distribution. Firstly, safety. Isolating the transformer from the ship's hull reduces the risk of electrical hazards. Secondly, flexibility. Pier-mounted transformers can be easily accessed for maintenance or replacement without interrupting ship operations. Thirdly, space saving. Mounting the transformer on a pier frees up valuable space on the ship. Fourthly, durability. Transformers designed for marine applications are built to withstand the harsh conditions at sea. It is important to consult with a qualified marine electrician or engineer to ensure that the specific transformer selected meets the requirements and safety standards for the intended application. When selecting a 15 kilovolt power transformer for ship power distribution, several technical aspects must be considered to ensure safe and efficient operation. The transformer's insulation class is crucial. It determines the transformer's ability to withstand voltage stresses without failure. Higher insulation classes provide better protection against voltage surges and transients, which are common in electrical systems. The insulation material should also be compatible with the environmental conditions, such as humidity and temperature variations typical of marine environments. The voltage regulation of the transformer is another important parameter. Voltage regulation refers to the change in secondary voltage from no load to full load conditions expressed as a percentage. A lower voltage regulation value indicates better performance, as it ensures a more stable voltage supply to the ship's electrical equipment. This is particularly important for sensitive electronic devices that require a consistent voltage level to operate correctly. The impedance of the transformer affects the fault current levels in the electrical system. A higher impedance limits the fault current, reducing the stress on circuit breakers and other protective devices. However, a higher impedance can also increase the voltage drop under load conditions. Therefore, the impedance should be carefully selected to balance these two factors. The transformer's cooling method is critical for dissipating heat generated during operation. Common cooling methods include air-cooled, oil-cooled, and water-cooled systems. Air-cooled transformers are simpler and require less maintenance, but may not be suitable for high-power applications or confined spaces. Oil-cooled transformers offer better cooling performance, but require regular oil testing and maintenance. Water-cooled transformers are the most efficient, but require a reliable water supply and a cooling system. The transformer should be equipped with appropriate protection devices to prevent damage from overloads, short circuits, and other abnormal conditions. Overcurrent protection can be provided by fuses or circuit breakers, which interrupt the current flow when it exceeds a predetermined level. Ground fault protection is essential to detect and clear ground faults, which can pose a serious safety hazard. Other protection devices may include voltage surge arresters, temperature sensors, and pressure relief valves. The transformer's core material affects its efficiency and performance. Common core materials include silicon steel and amorphous steel. Amorphous steel cores offer lower core losses, resulting in higher efficiency, but they are more expensive. The core material should be selected based on the trade-off between cost and performance. The transformer's enclosure should be designed to protect it from the harsh marine environment. The enclosure should be made of corrosion-resistant materials and should provide adequate protection against moisture, dust, and salt spray. The enclosure should also comply with relevant safety standards such as those specified by the International Electrotechnical Commission (IC) or the National Electrical Manufacturers Association (NEMA). The transformer's terminals should be properly sized and insulated to ensure safe and reliable connections. The terminals should be compatible with the ship's electrical system and should be accessible for maintenance and inspection. The terminals should also be protected from corrosion and mechanical damage. The transformer should be tested and certified to ensure that it meets the required performance and safety standards. Testing may include routine tests such as insulation resistance tests and voltage ratio tests, as well as type tests such as short circuit tests and impulse voltage tests. Certification should be provided by a recognized testing laboratory such as Underwriters Laboratories, UL, or Canadian Standards Association (CSA). In addition to these technical aspects, there are also several practical considerations to keep in mind when selecting and installing a 15 kV power transformer for ship power distribution. The transformer's size and weight should be compatible with the available space and lifting capacity on the pier and the ship. The transformer should be located in a well-ventilated area to prevent overheating. The transformer should be accessible for maintenance and inspection. The transformer should be protected from physical damage and unauthorized access. The installation of the transformer should comply with all applicable codes and regulations, including the National Electrical Code (NEC) and the American Boat and Yacht Council (ABIC) standards. The installation should be performed by qualified personnel with experience in marine electrical systems. The transformer should be regularly inspected and maintained to ensure its continued safe and efficient operation. Maintenance should include regular cleaning, visual inspections, and electrical testing. Any problems or defects should be promptly corrected. The transformer's operating temperature should be monitored to prevent overheating. Overheating can damage the transformer and reduce its lifespan. The transformer's oil level, if applicable, should be checked regularly to ensure that it is within the proper range. Low oil levels can lead to overheating and damage. The transformer's bushings and connections should be inspected for signs of corrosion or damage. Corroded or damaged bushings and connections can cause electrical faults. The transformer's grounding system should be inspected to ensure that it is properly connected and functioning. A faulty grounding system can pose a serious safety hazard. The transformer's protective devices should be tested regularly to ensure that they are functioning properly. Faulty protective devices can fail to protect the transformer from damage. When specifying a 15 kV transformer for shipboard use, it is also important to consider specific standards and regulations that govern marine electrical systems. The International Electrotechnical Commission (IC) publishes a range of standards relevant to marine electrical installations, including IEC 60092, which covers electrical installations in ships. This standard provides detailed requirements for the design, construction, and testing of electrical equipment used on board ships, including transformers. It addresses aspects such as insulation levels, temperature ratings, and environmental protection. The American Bureau of Shipping (UBS) is a classification society that sets standards for the design and construction of ships and offshore structures. ABS publishes the rules for building and classing steel vessels, which includes requirements for electrical systems. These rules cover topics such as power distribution, wiring, and equipment selection. Compliance with ABS rules is often required for ships to be certified for operation. The United States Coast Guard (USC) also has regulations that apply to electrical systems on ships operating in U.S. waters. These regulations are found in Title 46 of the Code of Federal Regulations (CFR). Subchapter J of Title 46 covers electrical engineering, and it includes requirements for transformers and other electrical equipment. These regulations address safety issues such as grounding, overcurrent protection, and wiring methods. When selecting a 15 kV transformer, it is essential to ensure that it meets all applicable standards and regulations. This may require obtaining certifications from recognized testing laboratories such as UL or CSA. It is also important to work with a qualified marine electrician or engineer who is familiar with the relevant codes and standards. In addition to these regulatory requirements, there are also several best practices that should be followed when using 15 kilovolt transformers in marine applications. Firstly, it is important to properly size the transformer to meet the load requirements of the ship. An undersized transformer can overheat and fail, while an oversized transformer can be inefficient and costly. Secondly, the transformer should be located in a well-ventilated area to prevent overheating. Adequate ventilation is essential for dissipating heat generated by the transformer. Thirdly, the transformer should be protected from physical damage and exposure to harsh environmental conditions. This may involve installing the transformer in a weatherproof enclosure or providing additional protection against corrosion and vibration. Fourthly, the transformer should be regularly inspected and maintained to ensure its continued safe and reliable operation. This includes checking the oil level, inspecting the bushings and connections, and testing the protective devices. Fifthly, all electrical work on the transformer should be performed by qualified personnel who are familiar with the relevant safety procedures. Working with high voltage equipment can be dangerous, and it is important to take precautions to prevent electrical shock and other hazards. The selection of a 15 kilovolt transformer also depends on the specific application and the characteristics of the ship's electrical system. For example, some ships may require transformers with special features such as harmonic filtering or voltage regulation. Other ships may have limited space or weight restrictions, which can affect the choice of transformer. It is also important to consider the long-term operating costs of the transformer, including energy consumption, maintenance, and replacement. High-efficiency transformers can save energy and reduce operating costs over the life of the equipment. In summary, using a 15 kilovolt power transformer for ship power distribution is feasible, but it requires careful consideration of several technical and practical aspects. The transformer must meet all applicable standards and regulations, and it must be properly sized, installed, and maintained. By following these guidelines, it is possible to ensure the safe and reliable operation of the ship's electrical system. Furthermore, one needs to carefully choose the type of transformer to deploy. There are mainly two types of transformers, dry-type and liquid-filled. Dry-type transformers are ideal for indoor applications or locations with strict environmental regulations because they use air for cooling and insulation. They do not use oil, which eliminates the risk of leaks and reduces maintenance requirements. Liquid-filled transformers, which use oil or other dielectric fluids for cooling and insulation, are more efficient and have higher overload capacity. They are suitable for outdoor applications and harsh environments, but require regular maintenance to prevent leaks and ensure proper operation. The choice depends on the specific needs of the ship's power distribution system. The location where the transformer will be installed plays a critical role in its selection and setup. Pier-mounted transformers are typically installed outdoors and require robust protection against environmental factors such as moisture, salt spray, and extreme temperatures. The mounting structure should be stable and capable of supporting the transformer's weight and withstanding vibrations from nearby machinery or ship movement. The location should also provide easy access for maintenance and inspections, with sufficient clearance for personnel to work safely around the equipment. If the transformer is to be installed on the ship itself, space and weight constraints become important factors. Shipboard installations require compact and lightweight transformers to minimize their impact on the ship's stability and cargo capacity. These transformers must also be designed to withstand the constant motion and vibration of the vessel, as well as potential exposure to corrosive marine environments. Safety is paramount in any electrical installation, but it is especially critical in marine environments where the risk of electrical shock and fire is higher. Grounding is essential to prevent electrical hazards. The transformer should be properly grounded to the ship's hull or a dedicated grounding system to provide a low-resistance path for fault current. Overcurrent protection, such as fuses or circuit breakers, should be installed to protect the transformer and downstream equipment from overloads and short circuits. Regular inspections and testing should be conducted to ensure that all safety devices are functioning correctly. A maintenance plan should be in place to keep the transformer in good working condition. This includes regular inspections, cleaning, and testing to identify and address potential problems before they lead to failures. The maintenance schedule should be based on the manufacturer's recommendations and the specific operating conditions. Records of all maintenance activities should be kept to track the transformer's performance and identify any trends or patterns that may require attention. Proper cable management is also crucial for safety and reliability. Cables should be properly sized and insulated to handle the expected current and voltage levels. They should be routed in a way that minimizes the risk of damage from abrasion, bending, or exposure to harsh environments. Cable supports and clamps should be used to secure the cables and prevent them from moving or vibrating. Proper labeling and identification of cables and terminations can help prevent errors during maintenance and troubleshooting. Surge protection is critical to safeguard the transformer and connected equipment from voltage spikes and transients caused by lightning strikes, switching operations, or other electrical disturbances. Surge arresters should be installed on both the primary and secondary sides of the transformer to divert excess voltage to ground, protecting the insulation and preventing damage. The surge protection system should be designed to withstand the expected surge levels in the marine environment. To summarize, the use of a 15 kV power transformer for ship power distribution is feasible and can offer several advantages, but it requires careful planning, design, and implementation. It is crucial to consult with qualified marine electrical engineers and adhere to relevant standards and regulations to ensure the safety, reliability, and efficiency of the installation. In the context of a ship's electrical distribution system, a 15 kV transformer serves a critical role by stepping down the voltage from a higher level, often supplied by shore power or an onboard generator, to a lower voltage suitable for the ship's various electrical loads. These loads can include lighting, HVAC systems, navigation equipment, propulsion systems, and other essential services. The transformer acts as a voltage regulator, ensuring that the ship's electrical equipment receives a stable and consistent voltage supply, regardless of fluctuations in the input voltage or changes in the load demand. This stability is essential for the reliable operation of sensitive electronic devices and for preventing damage to electrical equipment. When selecting a 15 kV transformer for shipboard use, it is also important to consider the specific requirements of the ship's electrical system. For example, some ships may require transformers with special features such as harmonic filtering or voltage regulation. Other ships may have limited space or weight restrictions, which can affect the choice of transformer. It is also important to consider the long-term operating costs of the transformer, including energy consumption, maintenance, and replacement. High-efficiency transformers can save energy and reduce operating costs over the life of the equipment. Let's delve a bit deeper into the technical specifics. Firstly, understanding the transformer's vector group is crucial. The vector group designation indicates the phase shift between the primary and secondary windings. Common vector groups include diene-11, yn-done, and diene. The choice of vector group depends on the specific requirements of the electrical system and the need to minimize harmonic currents. Secondly, tap changers. Tap changes allow the voltage ratio of the transformer to be adjusted to compensate for voltage variations in the supply network. Tap changes can be either on-load or off-load. On-load tap changes can be adjusted while the transformer is energized, while off-load tap changes require the transformer to be de-energized. The choice depends on the frequency with which voltage adjustments are required. Thirdly, transformer protection relays are vital. These relays protect the transformer from faults such as overcurrent, overvoltage, and earth faults. Common protection relays include differential relays, overcurrent relays, and voltage relays. The relay settings should be carefully selected to ensure that the transformer is adequately protected without causing nuisance tripping. Fourthly, the transformer's thermal management. Monitoring the transformer's oil temperature and winding temperature is essential to prevent overheating. Temperature sensors can be installed to provide real-time temperature readings. Cooling fans or oil pumps can be used to enhance cooling and prevent excessive temperature rise. Fifthly, insulation oil quality. For oil-filled transformers, it is important to monitor the quality of the insulation oil. Oil samples should be taken regularly and tested for parameters such as water content, acidity, and electric strength. Oil treatment or replacement may be necessary to maintain the oil's insulating properties. Sixthly, noise levels. Transformers can generate noise due to the vibration of the core unwindings. Noise levels should be minimized to comply with environmental regulations and to prevent disturbance to personnel. Noise reduction measures may include the use of vibration damping materials and acoustic enclosures. Seventhly, the transformer's ability to handle harmonics. Harmonic currents can cause overheating and other problems in transformers. Transformers should be designed to withstand the expected harmonic levels in the electrical system. Harmonic filters may be necessary to reduce harmonic currents. Eighthly, the transformer's seismic withstand capability. Ships operating in earthquake-prone areas should use transformers designed to withstand seismic forces. Seismic qualification should be based on recognized standards such as IEE 693. Ninthly, the transformer's overload capacity. The transformer's overload capacity indicates its ability to handle short-term overloads without damage. The overload capacity should be sufficient to meet the expected peak load demands of the electrical system. Tenthly, the transformer's efficiency class. Energy-efficient transformers can save energy and reduce operating costs. The efficiency class should comply with recognized standards such as IEC 60076-20. There are several types of tests that need to be conducted on power transformers before they are put into service. 1. Insulation resistance test. This test measures the resistance of the transformer's insulation to ensure that it is free from defects. 2. Turns ratio test. This test verifies the turns ratio of the transformer to ensure that it is correct. 3. Polarity test. This test determines the polarity of the transformer windings to ensure that they are properly connected. 4. No load loss test. This test measures the losses in the transformer when it is energized but not loaded. 5. Impedance test. This test measures the impedance of the transformer to determine its ability to limit fault currents. 6. Temperature rise test. This test determines the temperature rise of the transformer under full load conditions. When installing a power transformer, there are several important safety precautions that should be followed. 1. Only qualified personnel should be allowed to install or maintain power transformers. 2. Always to energize and lock out the transformer before performing any work. 3. Use appropriate personal protective equipment, PPE, such as gloves, safety glasses, and hard hats. 4. Follow all applicable safety codes and regulations. 5. Ensure that the transformer is properly grounded. 6. Never work on a transformer in wet conditions. In addition to the above, here are some other technical considerations. Firstly, the inrush current must be considered. When a transformer is energized, it can draw a large inrush current that can trip circuit breakers or damage the transformer. The inrush current can be limited by using pre-insertion resistors or other techniques. Secondly, parallel operation of the power transformer. Transformers can be operated in parallel to increase the capacity of the electrical system. However, the transformers must have the same voltage ratio, vector group, and impedance to operate properly in parallel. Thirdly, spare parts availability. It is important to ensure that spare parts are readily available for the transformer in case of failure. This can minimize downtime and reduce the cost of repairs.